Hello everyone and welcome. In this video we're going to talk about the dilogarithm. Okay, so especially we're going to prove some identities involving this function. Okay, so we're going to start with the definition. So we define the dilogarithm function as Li sub 2 of z equal the sum as n goes from 1 to infinity of z to the n divided by n squared. And this power series converges inside the open unit disk in the complex plane. Now, of course, this definition is restricted. We can actually define the dilogarithm on a much bigger domain by using the integral definition. So this is the analytic continuation of the dilogarithm. So we can define it on the complex plane minus the interval 1 to infinity. And this is the definition we're going to be using. Okay, as I was saying, we're going to derive or we're going to prove some identities involving the dilogarithm function. So the first identity was already proved in my previous video about polylogarithm, but I am going to give a different proof here using the second definition, the one involving integral. So the identity we're going to prove here, so the first identity is Li2 of z plus Li2 of negative z equals 1/2 of Li2 of z squared. Now, by definition, we just saw that Li2 of z is negative integral from 0 to z of log of 1 minus t divided by t dt. Now, we just use the definition here. Now, in the second integral, what we want to do is change t into negative t. So, after changing variables, so we get the integral from 0 to z of log of 1 plus t divided by t dt. Now that we have the same limits of integration everywhere, we can combine these three integrals into a single integral and then use a property of logarithms called the product rule. So using the product rule, the sum of two logarithms becomes the logarithm of the product of the two arguments. And 1 minus t times 1 plus t is simply 1 minus t squared. And then here, we make a change of variable by setting u equals t squared. And of course, dt over t becomes du over 2 times u. The new limits of integration are going to become 0 and z squared. So now, if we factor 1/2 out, we get negative 1/2 integral from 0 to z squared of log of 1 minus u over u du. And this is precisely 1/2 of Li2 of z squared. Okay, so we're done with this identity. Let's move on to the second identity. So the second identity is Li2 of 1 minus z plus Li2 of 1 minus 1 over z equals negative the square of log of z divided by 2. We're going to start with Li2 of 1 minus z to the negative 1. By definition, it is given by this integral. And what we want to do here is perform the following change of variable. We're going to put t equals 1 minus 1 over 1 minus u. And of course, u is going to be given by a similar formula. So u will be equal to 1 minus 1 over 1 minus t. Now the new limits, you can check that, are going to become 0 and 1 minus z. So we're going to get that this is equal to negative the integral from 0 to 1 minus z of negative 1 minus u divided by u times negative log of 1 minus u to the negative 1 divided by 1 minus u squared and du. After simplifying, and of course we have to use uh, the power rule for the logarithm, and we're going to get the integral from 0 to 1 minus z of log of 1 minus u divided by u minus u squared. Well, u minus u squared is simply u times 1 minus u, and we can use a partial fraction decomposition here, and we get the integral from 0 to 1 minus z of log of 1 minus u over u plus log of 1 minus u over 1 minus u du. Using the linearity of integrals, we get the integral from 0 to, so we get the sum of these two integrals. Now the first integral is simply negative Li2 of 1 minus z. The second integral can be computed, and we're going to get negative 1/2 of the square of log of 1 minus u, which we're going to take between 0 and 1 minus z. After evaluating, we're going to get simply negative 1/2 of the square of log of z. Now we just have to move the first term to the left hand side, and we're going to get the desired identity. Okay, now let's move on to the third identity. The third identity is Li2 of z plus Li2 of 1 minus z equals pi squared over 6 plus log of z times log of 1 minus z. Okay, so we're going to start with Li2 of z. So that's the definition. And then we're going to split the integral from 0 to 1 plus the integral from 1 to z. Now the first integral is simply Li2 of 1. And Li2 of 1 we know is theta of 2, which is pi squared over 6. And then for the second integral, we're going to perform a change of variable by setting u equals 1 minus t. So we're going to get negative integral from 0 to 1 minus z of negative log of u divided by 1 minus u du. We perform an integration by parts now. As we integrate by parts, we get theta of 2 minus log of u times log of 1 minus u taken between 0 and z plus the integral from 0 to 1 minus z of log of 1 minus u over u du. Now that last integral is simply negative Li2 of 1 minus z. Okay. Now let's look at the log, the product of the two logs. We can easily evaluate that at z, because z is actually in the complex plane minus the interval going from 1 to infinity. So remember that we cannot evaluate a log at 0, so we have to take a limit. But the limit of this product, of the limit of log u times log of 1 minus u, as u goes to 0 is actually 0, because log of 1 minus u is equivalent to u. So we end up with theta of 2 minus log of z times log of 1 minus z minus Li2 of 1 minus z. And then we just have to move the last term to the left hand side and replace theta of 2 by pi squared over 6. And that's precisely the Basel problem. So we get the desired identity. Now let's move on to the fourth identity. So we want to prove that Li2 of negative z minus Li2 of 1 minus z plus 1/2 of Li2 of 1 minus z squared is equal to negative pi squared over 12 plus log of z times log of z plus 1. Okay, so we're going to start with the left hand side, and we're going to use two identities here, the first identity and the third identity. Using the first identity, we can express Li2 of negative z in terms of Li2 of z and Li2 of z squared. So, and everything else is going to be unchanged. So Li2 of negative z is simply negative Li2 of z plus 1/2 of Li2 of z squared. Now we're going to combine Li2 of z and Li2 of 1 minus z, and the remaining terms are also going to be combined. So we get to get the following. Now we can use the third identity. So using the third identity, recall that the third identity tells us that Li2 of z plus Li2 of 1 minus z is equal to pi squared over 6 plus log of z times log of 1 minus z. So using that identity, we end up with negative pi squared over 6 minus log of z times log of 1 minus z plus 1/2 of pi squared over 6 plus log of z squared times log of 1 minus z squared. Now we use the power rule for the log, and then we simplify. After we do that, we end up with negative pi squared over 12 minus log of z times log of 1 minus z plus log of z times log of 1 minus z squared. Now we're going to factor log of z. Okay, and then we have these term inside brackets. So that's a difference of two logarithms. So we can combine those two terms into a single log by using the quotient rule. And then note that 1 minus z squared over 1 minus z can be simplified because 1 minus z squared is simply 1 minus z times 1 plus z. So after simplifying, we get the desired identity. Okay, now we just have the last identity, the fifth identity, and it is Li2 of z plus Li2 of z to the negative 1 is equal to negative pi squared over 6 minus the square of log of negative z divided by 2. So we're going to start with Li2 of z to the negative 1. Now, we know that it's going to be negative the integral from 0 to z to the negative 1 of log of 1 minus t divided by t dt. Now, we want to split our integral into two parts. The first integral is going to be the integral from 0 to 1, and the second one is going to be from 1 to z to the negative 1. The first integral is simply theta of 2, or Li2 of 1. Now, for the second integral, we're going to perform a change of variable. We're going to put u equals t to the negative 1, or if you want t equals u to the negative 1. And then the integral is going to turn into the integral from 1 to z. So plus integral from 1 to z of log of 1 minus u to the negative 1 divided by u du. Now let's look at the argument of the log. We're going to write it as 1 minus u over negative u. And then we're going to use the quotient rule. Okay? So that's what we're going to get after using the quotient rule. Next, we are going to use the linearity of the integral. There, after using the linearity. Now, the last integral can be computed. Let's look at the first integral. The first integral, well, can be simplified as a difference of two Dilogarithm values. So it's going to be Li2 of 1 minus Li2 of z. Okay? And as we compute the last integral, we're going to get negative 1/2 the square of log of negative u, which we're going to evaluate between 1 and z. So after evaluating, we get, and keep in mind that Li2 of 1 is simply theta of 2. Theta of 2 plus theta of 2 twice theta of 2. So, and log of negative 1 is simply log of e to the I pi. So it's going to be simply I pi. I pi squared is going to be simply negative pi squared. Okay, so we're going to simplify that. So everything else is just some computation. So we're going to compute now. I pi squared is simply negative pi squared, but there's a negative in front of it, and there's a negative in front of the fraction. So we're going to end up with negative pi squared over 2 minus the square of log of negative z divided by 2. Now, if you combine pi squared over 6 and negative pi squared over 2, we get exactly a negative pi squared over 6. Now, all we have to do is bring the first term to the left-hand side to get the desired identity. And this is the end of the video. Thank you for watching, and see you next time. Bye.